Hi there, welcome to your lesson on common and natural logarithms. On your calculator, you may have noticed a logarithm button and also another button near it that says ln. That's a natural logarithm. We're going to look at these two most common types of logarithms in this lesson. So what are common and natural logarithms? Again, if we have our TI-84 graphing calculator, you will see on the side here besides 7 and 4 right over here, the log button again and the natural log button. So if these logs have their own buttons, they must be the most important of all the logs, right? Because we know a log can take on any base. However, there's these two that are the most important. Let's take a look at them. So for example, if somebody asks you to evaluate or find the value of log base 10 of 5, this one is a log base 10, and that is what a log is. If you just see log written like this with no base, that tells you it is log base 10. Alright, so when we just see log, it means log base 10. Because log base 10 is so important, it just becomes this common log that we really don't need to write the base. And we'll take a look at why that is in just a moment. But for now, know that when you see no base, it means base 10. And that also means it's that button on your calculator. So if you punch that on your calculator, we'll check what we get. So I'm going to punch in log here and then 5, because again log just means log base 10 equals, or enter, 0.6989. So that equals this value here. Now let's think about y for a second. Remember when you have log form that we are asking 10 to what power produces a 5? Well, we know 10 to the first power would be 10, but now we have a result less than 10. So it must be 10 to a power less than 1 that produces a 5, and that's what we have here, 10 to this power. Okay, let's look at another one. So next one I have for you is this, log base e, and you might be wondering, what is e? And we'll talk about that in a minute as well. E is a very important irrational number, like pi, for example. E is 2.718, blah, 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 blah. Decimals go forever, no patterns. It's an irrational number. It's a very important number, so important that a log with base e also gets its own button. And log base e is actually ln. So we see that ln button here. That means natural log, and that means the same thing as log base e. So don't forget that this means log base e. Okay, so we're going to punch down our calculator as well and see what we get. So ln, I'm going to press the natural log button of 7 and enter, and I get a result of 1.95 about, if I round it, so 1.95. Okay, so those are those two buttons and what they represent. So again, two most important logs, the ones with base 10 and the base e, and we'll see why in just a moment. Let's look at one more. So what if you have a log with a different base? This one, obviously you cannot have a button for every possible base on your calculator. So we learned something in the last lesson which helps us deal with this, and that is called the change of base formula. We can always take a log of any base and change it to any other base. And the easiest base to change it to is 10, because we have that button ready for us right there. So let's change this to base 10. And the way that works is you rewrite this as a division of logs with the base that you want. So I put base 10 here, and then this number goes here, and then this number goes here. Alright, if you remember that rule, it's going to make things easier for you, because on our calculator that's pretty easy to enter that. So let me try that now. First of all, to get a fraction on our calculator, if you don't remember, you can press alpha, y equals, and then choose number 1, n over d. Now I have a fraction. Okay, so log base 10, which is just log of 8, and then divided by log of 3. Enter. Notice the number's answer is 1.89, so that works out to 1.89. Now, some calculators do have the ability to create logs with different base. A lot of simple calculators cannot, so you have to use this to solve something like this. But our graphing calculator, you can enter logs with different base. That doesn't mean there's a button for it, but there's a way to enter it, so let me show you that now. So we can do that by pressing the math button, and then scrolling down the list. If you go down the list a little bit, you'll see log base, and there it is, log base. So I'm going to enter that. Notice now I can enter any base I want, so I'm not limited to just log base 10. So I'm going to put log base 3, and then I'm going to put of 8. And that answer should be identical to what we got here, because this and this are equivalent. So let's check. And there it is, we see the same answer. Great, so maybe your calculator can allow you to enter different bases. Experiment, see what you can do. Okay, so now, why are these so important? But let's recap first, again, what we've come up with here. A common logarithm is a log base 10, and it can just be written like this, with no base. A natural logarithm is a log base e, and it can be written, by the way, e is the number 2.71828, etc., 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 and it can be written as ln x natural log. Okay, so let's try applying what we just learned to these problems here. Grab your notebook if you haven't yet. Let's note this down and let's try this together, and then you're going to do a lot of practice in this assignment. So first one here. We know when we have to evaluate a log, first we say it equals x. Like we want to know what does it equal. So it equals x, okay? And we're going to find out what this equals by solving for x. This can be changed to exponential form. So 10 to the x equals 100. We know 100 is actually 10 squared. So we know that 10 squared must be 100, x must be 2. Now a lot of students look at that and they say, okay, I got an answer for x. Don't forget that the answer we found here is actually what this equals to. So now we know log of 100 equals 2. And that makes sense because log of 100 is log base 10. So you're thinking 10 to what power makes 100? And we know that power must be 2 because the answer to the log is the exponent, right, that you'll put on the base. So again, log base 10 of 100 right here. We're saying 10 to what power produces this, and that power must be 2. Great, let's try the next one. Here we can write that like that, log base 10 of 1 over 100 equals x. Okay, we're going to solve what, so you're thinking in your head, what power on 10 gives you this? And if you're already pretty accustomed with the stuff we've been doing with laws of exponents, maybe the answer is already obvious to you. You're already thinking 10 to some power gives you this. What is that power? Well, let's rewrite this in exponential form to see. So 10 to the x equals 1 over 100. We know we can bring that 100 up and make it a negative exponent, and it's also 10 squared on the bottom. So 10 squared comes up, becomes 10 to negative 2, therefore x is negative 2. And maybe that's what you're thinking when we're in this step, when I said 10 to what power gives you this? Well, if you're thinking 10 to the negative 2, that makes sense, because that means 1 over 10 squared, and 1 over 10 squared is 1 over 100. So I hope you're at the point where you can look at this and already think of the answer with these. All right, next one. We see a decimal here. These ones, you need to be able to convert this into a fraction. And this one can be converted into 1 over 10,000. This is 1/10,000th, so that's what we have here. So now again, you're thinking 10 to some power gives us this. And you know it's going to be a negative power because this is in the denominator. So now it's just a matter of determining 10 to what power creates this. So again, 10 to some power equals this. This comes up, and this is actually 10 to the 4th, so it's negative 4, because when that comes up, it's a negative 4th power. Great, that makes sense. 10 to the negative 4 power gives us this. Next one, now we're going to do natural logs. So here's ln, natural log of e to the 5th. Now don't be confused here. I see ln and I see e. It's important to know that there's going to be two e's here because ln can be rewritten as log base e. So I rewrote this as log base e, but I still have e to the 5th here. So now this, again, when you're reading this, you're thinking in your head, e to some power produces e to the 5th. And again, I hope the answer is clear. But if we write this in exponential form, we have e to some power, e to the x, equals e to the 5th. And that means that power, that x value must be 5. Okay, let's look at this one. In this one, then we see log, so that means log base 10. Now we're thinking 10 to some power is 8.5. Okay, so this one we cannot do easily like the other ones. We'll need our calculator for this one. But let's do some logic first. 10 to what power produces 8.5? Well, we know again that 10 to the first power would be 10. So that means the answer to this must be some power less than 1, because 10 to the 1 would be 10. So it must be something just less than 1. Let's check on our calculator, because this one we cannot do without our calculator. So I'm going to do log of 8.5. And we can see the answer is 0.929. Hey, that makes sense. Something very close to 1, but not quite 1. Because 10 to some power less than 1 gives you that. Last one here, now this is natural log again. We're going to change it to log base e. Now we're thinking e to some power equals 22. That one again, you'll need your calculator. So on your calculator, you press log, natural log, 22. Close that, and we have this, 3.09. Great. So let's jump from there and take a step back in history. What did people do before calculators and computers? Let's say you had no computer, no calculator. In other words, you had no computing power. You had no way to calculate large things. For example, like this. Let's say you had to multiply 637 by 1,284. Not a difficult multiplication if you know long multiplication, but let's say you want to avoid doing long multiplication, or let's say you had numbers much bigger than this and the long multiplication was very, very tedious. Well, here's a way that people dealt with this, and logs are at the heart of this. It's a part of the reason logs were created, to help us do large multiplications. Back in the 1600s, mathematicians, astronomers, scientists, they're looking at very large numbers for the first time. They were looking at distances and weights in space, and you need to multiply and convert really big numbers. So imagine you had two really big numbers multiplied and you had to figure out what it is, and you had no calculator. So here's the approach. You can change both of those to scientific notation, first of all. This is 6.37 times 10 to the second power, because this is like 100, it would move the multiple decimal twice. And this one is 1.284 times 10 to the third power. So now we've converted like that. Now we can actually apply a log to both sides. We put log here, log here. Now there's a rule in logs. When you have a log and you are multiplying, all those multiplications can be turned into the addition of single logs. So log of this thing plus log of this thing plus log of this thing plus log of this thing. So each of the multiplied things became its own log. We can look more on those rules later, but for now know that that's a main rule that has been developed with logs, and it works every time. So this simplifies things, because over here, for example, remember log here means log base 10. So we're thinking 10 to some power creates, well, this is 100, right? So that must become 2, because 10 to the 2 is 10 to the 2. And how about here? What's this going to become? Well, that must be 3, because, again, there's a base 10 here. 10 to some power is equivalent to 10 to the third. It must be 10 to the third power. All right, and the next step with that is, okay, so we have that. We converted that to 2. We converted this to 3. But we still have these logs. And here's where John Napier comes in. I told you about this famous mathematician. He spent a good part of his life calculating all kinds of logs and making books and books and books of tables where they had, basically you could flip to a page in this book and find out, okay, log of 6.37, what is it? And he had calculated already, so you would just find that calculation in the book. So this was kind of like a book that is a calculator. It does all the calculations for you. They're done for you. You just check the book. It's like checking your calculator. So people would refer to that. So if you're here, here's a portion of that book, for example, and you can see log of 10 and equals this, or log of 11 equals this. There's actually a 1 that should be added in front here, so it'll be 1.0. Log of 10 is 1, so this is 1.0. Log of 11 is 1.04, and so on. Anyway, imagine pages and pages and pages of this. You would refer to that, you would get these answers. So for example, log of, oh, no, I don't think it's in here. Okay, so anyway, those, you would grab those numbers from the table, so you have this number here, and for that you have this number. And now you can solve that. Combine those numbers. Those numbers have been combined, and we have this. Now this, we can convert back to exponential form, because we know this is log base 10. So we can write a equals 10 to this power. And again, these values could be found in these books of tables, and therefore now you have an answer. So you found an answer for your original question, which was, if we go back, 637 times 1284. And that answer is this power, which is interesting. Okay, and that brings us to a later development. People said, okay, well, we had these books of tables, but let's say we had this and we wanted to use another tool. So a tool called a slide rule was developed, and a slide rule allows you to convert numbers very quickly. So for example, I have a slide rule shown here, and maybe this is something, if you have some parents that were in school, I don't know, in the 70s even, or 60s, I'm not sure if your parents were in school at that time, but they may have used slide rules, because these were days before calculators, and slide rules were used like calculators. And basically there's a portion of this ruler that slides left and right, and you can calculate different things with it. We're not going to get into those details, but there is a video in our Explore section for today's lesson, and you can check out that video. It's a short one, and it explains how it works. It's really interesting stuff, so check it out. But for now, let me show you this. We have, for example, log of 1.284. I want to find that in the slide rule. So D here is decimal values. So I'm going to go to 1.284 on the decimal scale. So that would be, oh, I'm going to zoom in. On the decimal scale here, 1.284 would be somewhere in here. And then we go down to this scale below it, which if you look back on this ruler is L, which is logarithm scale. So again, I went to 1.284 here, and then I see on the log scale, it's like 1.09, and again, this is this. It's by a power of 10, but it's the same value, 1.09. So that's just a basic example of how people actually use these rulers to convert numbers. And then you can get those answers, add them up, and then you have your answer. All right, so we just saw a little bit of history where we went from log tables to slide rules and how logs have helped us do complicated calculations in an easy way. Of course, we looked at it in a very simple way. You can study all this on your own and you'll be very intrigued to see the details of that. So now let's jump back to the number e, because we said that natural log, the log of base e, is a very important one. Let's give a little history here. E is sometimes called Euler's number, after the Swiss mathematician Leonhard Euler, not being confused with this other character which represents another constant that he and somebody else are credited with. All right, so Euler's choice of the letter E or symbol E is said to have been retained in his honor. The number E has eminent importance in mathematics alongside 0, 1, pi, I. Okay, these are all these very key numbers clearly, some of them rational, some irrational. Like the constant pi, E is an irrational number, i.e. cannot be represented as a ratio of integers, and it is transcendental, which means it is not a root of any non-zero polynomial with rational coefficients. And the numerical value of e written to 50 decimal places is this. And of course, as it is irrational, it goes forever with no patterns in the decimals. Okay, so again, that tells us a little about the history, but doesn't tell us why it's important. Mathematically, it is important because of its place in mathematical analysis. Here we can see, and this is more in calculus, but eventually you'll learn more about these things as well. If we have a slope, this exponential growth curve here has this equation, e to the x, all right? You can have any number in the bottom of an exponential curve. This is e to the x. That curve has some very important properties. One of them being that if you put a value 1 into it and you arrive at this point, 1, 2.718, at that point, the slope of the curve is exactly e. And that happens with no other functions. So that's something that mathematically becomes very important, that the slope is the same as the y value at that point. And then we also see that the area under that curve, shown here in red, is also e. These are not coincidental things, and they're very important properties when we do higher mathematics. But I'll leave it there for you now, just to be intrigued, and you can go research things a little bit further. All right, let's do some work with logs. We're going to practice more with natural logs and logs with base 10. But here's some natural logs. So let's try b. In this one, we know we're trying to figure out what this equals. So I say it equals something, x. We can use properties of logarithms here. We know that ln is log base e. Don't forget that there's actually two e's here, right? Because this is log base e and this e to cubed is still here. Now e to the x is equal to e cubed. That means x must be 3. And that tells you that this original equation, or sorry, this original expression is equal to 3. That makes sense because when we see this, we say, the base is e. So we're thinking e to some power is the same as e cubed. And that means the power must be 3. That makes sense. All right, try the next 4 that you see here. Let's see if you can figure them out. Now let's check your work. So here's the next one, ln1 becomes this, and therefore x is 0, because the only way to get 1 is a power of 0. Okay, in f, let's see how you did here. We have that, which becomes this, e to the 1/3, and that means that x must be 1/3. That means that whole expression is equal to 1/3. All right, I'm going quickly through these, so pause if you need to, just to double check if you are doing the work correctly here. G, we have this, which becomes log base e of e to the -2 when you bring that up, and therefore e to the x equals e to the -2. So the power on e that produces this must be -2. And the last one looks like this. Bring that up, -1/2. Therefore, you can already see it. X must be -1/2. All right, great. This is now practicing what we know about exponents and logs all together. So it's good to practice these things together and just make sure you continue to feel more and more confident with this every day. All right, a few more for you to try. It never ends, I think, but let's try. So try B, C, and D, and let's check our work. So here's B, here's C, and oh, I'll have D on the next one, I think. Oh, do I? No, that is B, C, and D. Let me go back. Yeah, that is B, C, and D. So check your work carefully here. Notice in this first one, we've seen one like that before. We change that to a fraction. This is 10 cubed, bring it up 10 to negative 3, and then we solve. These ones are a little more simple, perhaps. Okay, let's look at the next ones. So E, F, and G. Let's see if you can do those. So here's E. Check your work there carefully. Here's F, and here's G. Okay, again, pause if you need to. I'm going to continue on. All right, H, I. Here's H. Notice in H now, we have something a little different, so I'll help you with this one. We have a 10 and a root 10. So first you have to combine those, right? So this is really, well, base 10, because now we're dealing with logs with base 10. And now this is 10 to the first, this is 10 to the half. We can combine those. We know when we multiply exponents, when we multiply these expressions, we can add the exponents. So we have 10 to the 3 halves when you add those, because this becomes 2 over 2. And you add it to that 3 over 2. So that tells you x must be 3 over 2. Okay, try the next one. Try, oh no, I is a little, not quite like that. K will be like that. So let's look at I, and then you try K in a similar way we did H here. So here's I, and we get this. Oh no, wait, actually no, that's what I'm doing. I'm leaving you to try these three here now, see if you can do them. So first one here, I looks like this, 2/3. Check your work carefully. Did you come up with that? I hope so. Notice this is 10 squared. And then rewrite it as a power, and then you should get to this pretty quickly. This one you need to combine these like we did here, so try it. Okay, the answer there is 4/3. And then this one here, again, you're going to have to change this to 10 to some power, then 10 to some power, combine them, and you should get this. All right, great job. Oh wow, it never ends, does it? Here's, try these 4 here first. Tell me what those answers are, and let's check. These are just going to show one step in the answer, so double check quickly. Again, pause if you need to, see how you did on those, and now try these 4 to wrap things up here. Okay, and then check your work here. So once again, you can pause to double check your work with these. At this point, if you've been keeping up with all the lessons, you are pretty quick, pretty proficient, and these come easily to you. If you're still struggling with them, I certainly can give you more practice. However, we have done a lot, and the goal was to really practice, practice, practice until it's almost automatic, which I hope you're feeling now. Great job. We'll see you soon.